These videos are a lead-in to a topic that is referred to as colligative properties. And these are properties that are due to the addition of a solute to a pure solvent. There's a couple of them. Vapor pressure is one of them. And what ties them together is that these are changes that are induced that are proportional to how much stuff you put in there, but not what it is, only how much. So here's the lead-in. So we talked about the vapor pressure equilibrium a couple videos ago, in that you've got a liquid and there is a certain pressure of the vapor phase above it in dynamic equilibrium. So any one atom or molecule is going back and forth between liquid or solid a billion times a second, but the number in the gas phase and the number in the liquid phase are constant once equilibrium is established. So what I want you to think about is, what if a solvent were added? Now think about this. The solvent, you can assume, is going to have some attractive interactions with the solvent. And the one thing that you need to know is that when you do this, if this solute is not volatile, it doesn't have a whole lot of, it doesn't have a high vapor pressure, and this is the case for, let's say, any ionic solute like sodium chloride. So it doesn't go in the gas phase. So the solute stays in the solution. What goes into the gas phase is pure solvent. Now what I want you to do is think about how that might change the equilibrium vapor pressure. How's that going to change the number of molecules that are in the gas phase, if at all? And while you're thinking about it, and for the sake of argument, again, assume there's some attractive interaction. So hit pause, think about this for a sec. And the answer is it should lower it. So if there is attractive interactions, this means that at a given temperature, some of the molecules that happen to be interacting with one of the solvent molecules that are interacting with one of the solute molecules are less likely to go into the vapor phase, because they have to, for them it would require a little extra energy, because they are more attracted to a solute than they would be to another solvent molecule. So the rate's going to slow down, which means that equilibrium is reestablished with a lower vapor pressure. And if you count, there are fewer gas phase molecules in this picture than there are in this one. Actually, in here, this is the final equilibrium. So now we've got far fewer in there. So the equilibrium vapor pressure actually decreases because of that increased attraction to the solute. The more solute molecule, solvent or solute ions, molecules, whatever they are that you've got in there, the bigger this effect is going to be, the greater the reduction in the vapor pressure. And the effect is more or less linear. So if you double the solute concentration, you will reduce this vapor pressure by half. Now, same pictures here. I want you to fill in the blanks. And this is going to be raising, lowering, stuff like that. So blank the temperature. Now let's say that you wanted to bring, so for this first question here, let's say you wanted to bring this vapor pressure back up to its original value. Would you do that by raising or lowering the temperature? You would need to supply more energy to overcome those stronger interactions, so you would need to raise the temperature. Now, recall, the normal boiling point of anything is the boiling point, is the temperature at which the vapor pressure is equal to the ambient pressure, whatever that happens to be. So 0.86 atmospheres in our lab. Now, so if we have to go to a higher temperature, what can we say about the normal boiling point of the solution relative to the pure solvent? Has it been raised, lowered, or is it unchanged? Well, it's been raised. So if you have to supply a higher temperature to get to the same pressure, you have raised the normal boiling point, or the temperature needed to get to any target pressure for that matter. So finish the statement. The temperature at which the solution has an equilibrium vapor pressure of 0.86 atmospheres is blank, greater, lesser, unchanged than the temperature at which the pure solvent has a vapor pressure of 0.86 atmospheres. And again, it's higher. So we have elevated the boiling point. Which is why this phenomena is called the boiling point elevation. And so the next question is, are other properties changed as well? And this salt truck is kind of a hint to another one. But first,